Okay guys, this is going to be Teacher Patrick. We're looking at skills for Coulomb's law. We're going to specifically start looking at the graphs. So firstly here we have a charged sphere, okay, and we've placed it now on top of a electric field displacement graph, okay. And now we know that basically the graph goes like this. But the question is, remember, because electric field is measured from the center of the sphere, what happens from the surface to there? What does the graph look like? And what we will see, and you'll see that it would be 0. So inside there is 0 electric field, okay. And if we go approach it from the other side, we would get something similar, okay. But if we compare it to the electric potential, once again we know the electric potential here, okay. We know the shape of the graph looks something like this, but inside the electric potential is constant. Okay, and when we look at this, we can use the R here, or the point where it starts decreasing, to get the radius. If they give us a graph like this, okay, the point where it starts decreasing is the radius, or here once again the point where it starts decreasing is the radius. Sometimes they don't give us any part of this graph. You might have to complete it, this one or that one, but the potential one is just a horizontal line from where that point starts decreasing, and the electric field one goes all the way to 0, okay, because there's no electric field inside. So here inside it's 0, and there inside the electric potential stays constant. Okay guys, the next skill is what we're going to look at is what do we do if we've got two charged objects and we've got a field in between and the potential in between. So here we've got two positive charge objects and we've got the field in between. So as I move my test charge from this side to that side, there is now going to be a resultant field. This one has a field, okay, and that one has a field, okay. And because the fields are in opposite directions, we'll most probably see that this one's field goes like that, and this one's field goes like this. Now, the reason that they're in opposite directions is because the electric field is a vector quantity. If we combine these two, so basically if we put them on the same one, the resultant field between the two would look something like this, where we're not starting from the radius here because we said there's no field line in between. Okay, so that's the radius of the one, and this would be the radius of the other one. Let's say it goes up to there. Okay, so why does this happen? If, let's say, they're equal in size, this one is repulsive and that one is repulsive if I've got a positive test charge in the middle. So at a certain point, the two repulsive forces will cancel each other out, and hence there would be 0 field. Now, what's the relationship between the gravitational or the potential, the electric potential, and the electric field? We know that the potential gradient, this gradient must be equal to the negative electric field. Okay, so how does that look? So if we look at it, we will now see, obviously we could get something like this. Okay, if they choose to draw it, here it would be more something like this, and let's say they're equal, and we can get something like that. Okay, this dip depends on the sizes and the distances, but this can be basically the general thing. Now guys, the relationship here is the gradient. Now at a certain point, this gradient needs to be 0, and that's why there's a turning point, because the gradient needs to be 0. Okay, so the V gradient, or the gradient in the potential, needs to be 0. It is the opposite sign, so what we see here, this is a negative gradient, okay, and the negative gradient times the negative gives me a positive value for the electric field. Here there's a positive gradient, so the positive gradient times that negative gives me a negative value for the electric field. The next type of question is what happens if these two fields are opposite. So what we will have is that when the test charge is close, there will be a big repulsion and a small attraction. And as we move our positive test charge there, the attraction will increase, but the repulsion will decrease. So basically what we get an overall field in that way. Okay, so here there will be no point along that line where the field is 0, and hence what we will have is we will basically have a graph that would look something like this. Okay, here's the two radii. So basically it would decrease. There would be a weaker point maybe, because remember electric field is inversely proportional to the radius squared, so it's not going to be proportional. There is going to be a point where it's not exactly the same. It might decrease and then it will increase again. There's no point where it crosses the y-axis because there's no point between a positive and a negative charge where the field is 0. Okay, so what would this look like in this case? So if we have this one, because there is two fields here, this time we're going to have something like this. Okay, and we can see that the value here, it's a constant negative gradient. The gradient decreases slightly and then increases again, but it's still a gradient. We know that the gradient of the potential is equal to the negative of the electric field. So here there's a negative gradient, but the negative gradient times the negative gives me a positive value for the electric field. Here, 0 gradient of the gradient, although we're going through 0, the gradient is still negative, so that gives me a positive value. Gradient negative, positive value. And hence here, what is the gradient again? Remember we said this also explains the 0 there and this constant value. If I have a constant value, the gradient of a constant value is 0, and hence there we have our zeros where we have our radii. Okay, so once again, if I need to get the radius, I can just look at those points. Okay, now we look at a question, guys. We're just going to analyze a few graphs. So here we've got a potential distance graph. Okay, so there are two objects. They don't tell us the charges of them. The one is positive. Okay, and now we can see firstly, if we look at this point here, okay, we can use that point to calculate the radius. Okay, we see that the slope is constantly negative, meaning there is no point between these two charges where the field is going to be 0. Hence they will have this opposite charges. So if this one is positive, that one would be negative. And we can also see here, if it's 30 centimeters, we can see that this one has a radius of 5 and this one has a radius of 3. Okay, so the slope constantly negative, and the slope of the potential gradient is equal to the electric field. So since there's never a point where the slope is 0, therefore the potential gradient of the electric field between them is never 0. The following question we're looking at here, we've got a electric field graph. Okay, we can see that the electric field starts on a positive. We've got point A and B, and we're varying the distance between them. Okay, here they are just 2 points. Okay, they're not 2 objects, so hence we do not see any radii because they're not circular objects. Okay, they're just point charges, so the charge has no radius here. It's not a surface of a nucleus or something like that. Okay, so guys, what we can see here is that it goes here, it decreases up to a point and then it increases again. So that tells me the fact that it decreases and then increases, that these two must have opposite signs, because the field never becomes zero. It never goes through the y-axis. Okay, sorry, I mean the x-axis. In the following question, we have an alpha particle and a proton. Both of them are positive, and if we move down, we'll see the individual electric fields of the two. Okay, so this is just the alpha particle in isolation. This is just the proton in isolation. Now, if we have to find the resultant, we know because both of them are positive, there should be a point where they are both 0. So if we quickly look at this point, okay, algebraically, when the top and the bottom is equal, then that should be 0. So we can see roughly about 12 here. There's 2 blocks above, 2 blocks below, okay. And now if we had to draw a resultant line, it should be a little bit lower there, okay. It should cross the 0 here around about 12, and it should go there. So we mathematically just subtract the values below, the blocks below from the blocks above, and we get a graph that looks like this. Hence, because they're positive, somewhere in between there's a point where the charges of the fields cancel each other because they're in opposite directions, and electric field is a vector quantity. Okay, lastly guys, here we have a potential energy. So this is the electric potential energy in joules. What does this mean? It means that we have the actual charge. Okay, so we've got a charge, point mass, and a proton. So this charge can be calculated from this graph. So if we have the whole potential gradient equation. Okay, so here we have our graph. It's very similar to the potential gradient graph. The only difference is now we have an actual value, so we can use these values. What we see here, we're just approaching, when the separation of the mass and the proton, okay, is decreased. So basically we're increasing the distance between them, and we see that we have to apply work. Okay, so when we go uphill, it does not happen automatically. I have to push it uphill. I have to do work. Okay, so the further I push them away from each other, the more work is done. Okay, so therefore they are attracting each other, and that charge needs to be negative. Okay, I hope you enjoy this and understand. Thank you. Bye bye.